Good evening, everyone, and welcome to this session of Geometry, Cosmology, Spirituality. Now, today I'm going to look a bit more at the golden ratio, and then we're going to draw some nice, simple rosettes from John Michell's watercolors. Now, let's begin with the slides. Now, I'm going to return to what I was talking about a couple of weeks ago on the full moon. And this is really the definition of the golden ratio. But also some visual examples just to make it clear. Now, I finished off the slides last week with this description of the doorways on the west front of Wells Cathedral. Now, here is that formula of the golden ratio, the square root of 5 plus 1 divided by 2. Now, if this is the first time you've seen this, don't worry, I'm going to explain it in a bit more detail shortly. Now, before I do that, we'll just have a visual example of it. So here we have a line, and that first longer stretch of the line that I've now demarcated with this marker, that is the square root of 5, which is here. It's actually 2.236 if you talk about it in more standard numbers. The square root of 5 plus 1. Then the whole thing needs to be divided in 2. Like so. Now what you end up with then is 1.618, and it's divided into 1 and 0.618, which is the golden section. Now, if we do the same thing on the other side, if you were watching a couple of weeks ago, you'll remember that these three marks in the middle, they give us the position of the three doorways on the west front of Wells Cathedral. If we think of the extreme ends of the line as being the extreme ends of the west front. And so we have this association of the golden section with a doorway moving from one, you could say, one level to another, or one place to another, in terms of spiritual symbolism. Now, I also showed this a couple of weeks ago. I'm just going to work through this again, just to remind you of what we did, because then I'm going to actually show you a model that I've made of this working in quite an interesting way in relation to an image of the Great Pyramid. Right, so the square root of 5 plus 1 divided by 2 equals 1.618. Now, as I mentioned a couple of weeks ago, the square root of 5 is this number here, 2.236. This number, if 2.236 is multiplied by itself, it makes 5. So that's what the square root of 5 is. Now, let's just take the divided by 2 off. And what we could say is that the square root of 5 plus 1 is equal to 1.618 plus 1.618. And when it gets divided by 2, then it just becomes a single 1.618. So we're just retracing the steps that I was talking about a couple of weeks ago. Now, let's take off this plus 1. So I now need to take a 1 off here. I'll take off this red number 1 and turn it into 0. So now we have what the square root of 5 is. This 2.236 is actually 0.618 plus 1.618. Now, these two numbers are intimately connected to the golden ratio, and particularly in relation to the number 1. Now, here's another way of looking at the formula in visual geometric terms. Square root of 5, this time we have a rectangle. So if this is 1, then this is the square root of 5, 2.236. And then the square is just 1, because obviously the square has an edge of 1 by 1. So this is the square root of 5 plus 1. Now, if we bring in this divided by 2, which is what gives us the golden ratio, in that goes. And so what we now have is a golden rectangle here and another golden rectangle here. So a golden rectangle as in 1 to 1.618. Now, if you take a square off a golden rectangle, then what you have left is also a golden rectangle. That's one of these particular qualities of the golden rectangle. Right, we're going to do the same thing on the other side. like so. And this is really what we drew 2 weeks ago, as well as putting in the opposing golden spirals that went with it. Now I'm going to show you how we can actually get to the square root of 5. This is just quite an interesting route that it's possible to take to the square root of 5 in terms of that rectangle that I just showed you, which was 1 by root 5. Now, if we have a square and the square has an edge of 1, then the diagonal of it is the square root of 2. So obviously the square root of 2 is the number which, if multiplied by itself, makes 2. Now I'm going to bring down that root 2 measurement down to the baseline so that we now have what could we call a root 2 rectangle. If that's 1, that's the square root of 2. Now this is the type of rectangle that the A paper that we work on is. So A1, A2, A3, A4, they're all root 2 rectangles. Now, I won't go any further with that, but that's just an interesting fact about root 2. Now from here, I'm going to now put in the diagonal of a root 2 rectangle. So in it goes, the diagonal of a root 2 rectangle is the square root of 3. So I'm going to bring that root 3 measurement down, like so. And so we now have a root 3 rectangle. If this is 1, this is the square root of 3. And in numerical terms, the square root of 3 is 1.732. It goes on to an indefinite number of decimal places. Now you can see a pattern's beginning to develop here because the diagonal that's going to go in for this root 3 rectangle is the square root of 4. So you can see how things are naturally progressing. Now the square root of 4 is 2, because of course if you multiply 2 by itself, you get 4. So if this measures 1, this diagonal here measures 2. Now we're going to bring that 2 measure down so that we make a root 4 rectangle. So this is 1, this is 2. So as you can see, this area here made up of these 3 extensions. Those 3 extensions together make a square. Now, as you can see, we're heading towards the square root of 5, which is what we want because that's what you find in the golden ratio. So the diagonal of a double square is the square root of 5. Like so. Now, the thing about this square root of 5 diagonal of a double square is that it has a very particular angle. It's just an odd angle, 26.565 degrees. And that is the precise angle of slant in all the passageways in the Great Pyramid. Now, obviously, this one here is horizontal, and this little bit down here is horizontal. But all of the other passageways, all of these ones here, they all run at that kind of angle, 26.5. I think it's just very slightly off 26.565 degrees. So what you can say about these passageways is that if you were to go 1 unit down, however far, then you could go 2 units across and you'd get back to the passageway again. So this is a very simple rational unit of measure that's used for these passageways, but the actual angle of, well, the line itself isn't irrational. It's the square root of 5, which is one of these incommensurable numbers that I've been talking about a lot during these sessions. So I'm bringing that square root of 5 measure down like so. And so we now have a root 5 rectangle. So we can say square root of 5, and then we say plus 1, like so. And then we have that square root of 5 plus 1 divided by 2. And we have what I showed you just a bit earlier with the golden rectangle. Now I want to talk about pyramid triangles. So we've just been looking at an image of the Great Pyramid. I'm very interested in pyramid geometry because of its apparent use in Gothic cathedral design. But a key thing here is that there are 2 different pyramid triangles which are virtually identical. Now, here are 2 images from my research about the cathedral here in Wales. Now, let's just get our bearings here. You see the Lady Chapel here, so you can see Lady Chapel, and this is the east end of the cathedral. Here we have it again here, slightly larger scale in this photo. And so you can see this octagonal area and this octagonal area are essentially the same place. But as you can see, this is Chapter House, that's the upper level, whereas this area, Undercroft, is the lower level. The staircase that you have going up to the Chapter House, here you can see just the beginning of the staircase because this is the lower level. So as you can imagine, what we're looking at here, the pyramid triangle, which goes from the center of the crossing of the cathedral to the threshold of the Lady Chapel and then up to the center of this octagonal area. It would appear as if it's the same pyramid triangle that's used in both cases. It's the same pyramid triangle that's marked out as we're looking at it on these two different versions of the plan. But in actual fact, these two triangles are used, or rather this one triangle is used in two different ways. Now this version of the pyramid triangle, and this the diagram we have here, is the diagram that was discovered by John Michell in 1970 or thereabouts, to do with the Earth and the Moon. So if this is the Earth, this circle here, then this one is the Moon. And that appears to be used. There's all sorts of lunar symbolism around the chapter house, 29.5 steps in this staircase, and more than that. So this is where the pyramid triangle is used in its rational form because it has a base of 11 and a height of 7. And that's how it works in John Michell's diagram. Now this triangle here, as you can see, it's exactly the same one, you could say, in terms of how it's marked out, but it's used in a different way in this particular instance. It's used as a golden ratio pyramid triangle. If this is 1, then this is 1.618. So you could say the whole baseline is 2. We'll say 1 to 1.618. Now, along with this is the sacristy area that I showed a couple of weeks ago. These two doorways marked in yellow, they're both at the golden section of their particular wall on which they feature. So you also have this golden ratio line going through a golden ratio doorway. This dotted line here is another golden ratio line because this is 1 to 1.618, and this goes through the golden ratio doorway. These red lines actually denote the fact that this is the golden ratio here between this point and this point. So it's this very well used golden ratio diagram. Now, these two pyramid triangles, they're used in different ways because they do different things. The golden ratio pyramid triangle obviously brings forth golden ratio measures and also polygon geometry that you get from the golden ratio, which is basically 5-fold and 10-fold symmetry. Whereas this one here, as I mentioned before, uses rational numbers. It's a base of 11 and a height of 7. But both of these pyramid triangles are used as if they're the same thing. Now, at this particular scale that we're looking at them in the cathedral at Wells, they're only probably about a quarter of an inch different in height. So the height as in from here to here, and from here to here. If we look at these two different pyramid triangles, they're only about a quarter of an inch different in height. So very easily, it's possible to use both of them as if they're the same triangle, but they do different things. They bring forth different types of geometry. Now I'm going to show you how exceedingly similar these two triangles are. Now I've actually used the same picture here for the two triangles because at this scale, they are basically the same size. They're probably about, I don't know, 1/10 of a millimeter, if I was going to use metric measure, different to one another. They're virtually identical. So the one on the left we'll say is the 11, base of 11 and height of 7. And this one we'll say is base of 2, and that's 1.618. So this is the golden ratio pyramid triangle. Now, if we say they've both got a base of 2, then the height of the triangle on the left would be 1.2727272727. It's one of those repeating decimals. Whereas the golden pyramid triangle would have a height of 1.2720. So as you can see, it goes all the way to the 4th decimal place before it shows its difference. So these are virtually identical, and this is why they can be used as if they're the same triangle, even though they're ever so slightly different. So this is the key point, really, that I need to make about my research in Wales. The pyramid geometry that's there uses these two different pyramid triangles that are as good as the same thing. Now, there is actually a third pyramid triangle that's a bit more different, but I won't go into that on this particular occasion. Now, let's sort of think about this in relation to the Great Pyramid. Which one of these pyramid triangles is used? Now, there is quite a simple answer to this, and that is that it's very clearly the 11-7 pyramid triangle. That base of 11 and height of 7 shows itself if you multiply both of those numbers by 40. So if you multiply 11 by 40, you get 440, which is the amount of Egyptian royal cubits in the baseline or well, the square base of the Great Pyramid. And that's 7, if you multiply it by 40, it goes up to 280 cubits, and that's the original height of the Great Pyramid. So very clearly it uses the 11-7 pyramid triangle, which is used in John Michell's diagram of the Earth and the Moon. But could it be said that perhaps it's also using this whole pyramid form as a golden ratio pyramid triangle as well? Right, this is what I'm going to show a model of. We'll start drawing in a second, but just let me get my model I've made to explain how this works. Right, I'll stop sharing my screen and switch camera on. Good evening, everyone, and welcome. Right, um, I shall spotlight myself for everyone. Okay, right. Now I'm going to get this model. I made this model. I worked this out years ago, and I haven't really sort of shown it to anyone. I nearly put it into an article, but I love it. It's a lovely little, really simple model that shows something very nice in relation to pyramid geometry and the square root of 5 that I was talking about. Change to my other camera again. Right, okay. Now this is mocked up with bits of cardboard and all sorts, but it does the job. Now here we have 1 by 2. So remember, I was showing you that gradually developing rectangle where you go up the square roots from root 2, root 3, root 4, root 5. And once we get to the root 4 rectangle, which is a double square, 1 by 2, then we can say that the diagonal of the double square is the square root of 5. Now, you remember, I was saying how this is that angle of slant of all the passageways in the Great Pyramid, 26.565 degrees up from the horizontal. Now, the thing about square root of 5, if you cast your mind back to what I was saying at the very beginning of the session, I was saying how the square root of 5 is 1.618 plus 0.618. Now, that is what is going on with this mark here that I've made. So what we have here is 1.618, and then from here to here is 0.618. Now, the other thing about this is that we have 3 numbers from the formula for the golden ratio. So square root of 5 plus 1 divided by 2, there's the square root of 5, there's 1, and here we have 2. Now we're going to use this sort of, visually to show what can happen here. Because the thing to point out is that if this is 1.618 and this is 1 and this is 0.618, then we can say that this together is 1.618. So this plus this is the same as this. So if we do this, we get a golden ratio pyramid triangle. Now, how lovely is that? So simple. So we have the slant of all the passageways in the Great Pyramid, and then we have a particular type of pyramid triangle, which possibly is used intentionally within the Great Pyramid. There is actually another thing that is in my book about, well, what I'm calling a pediment triangle, and that is what suggests that the golden ratio pyramid triangle is, as it were, intended within the Great Pyramid, because very clearly it's the 11-7 pyramid triangle that's used because of the 440 to 280 cubits measure. But I think it's possibly both at the same time, which is how it works in the cathedral at Wells too. Okay, now having done all of that geometry, um, I'm actually going to do something quite different for our drawing. It's still golden ratio geometry, but I'm going to do a couple of rosettes from John Michell watercolor. So I've talked about John Michell a lot in these classes, and I do a lot in my book. I might as well show you where he has the Earth and the Moon diagram. This book is called How the World is Made, according to Sacred Geometry. Really good book. It's the book he wrote just sort of as he was dying. So he died of cancer back in about 2009. So this was sort of his masterwork. And here you have that Earth-Moon relationship, which appears to be used in the design of the cathedral here at Wells, as well as at York and Southwell Minsters. But I think I'm going to do an online geometry sort of John Michell watercolors course. So I'll tell you about that. It'll be a course that I'll charge for, but I think I'm going to do that perhaps in a couple of months. I'll start doing that course online, and it'll be drawings like this. And we're going to actually do a couple of rosettes. This is such a good book. His watercolors are just wonderful. But let's just look at this one. I'm going to do a couple of these rosettes, this one and this one. Uh, nice simple drawings. You know, it's late at night. Well, it is for if you're in this part of the world anyway. So just something nice and relaxing for the new moon. Right, I've got a piece of A3. I'm actually going to fold this A3 into an A4. So you remember I said how if this is one, this is root two. Now the quality of a root two rectangle is that when you fold it in half, you end up with another root two rectangle. So if this is one, this is root two. That's just the particular quality that a root two rectangle has. Right, the reason why I'm doing this is because we're going to do a couple of drawings and we want to divide the circle up into 10 as well. So I'm going to do that one here and then put pinprick holes through, and then we can draw, well, we will have three places to draw here, here, and here. I'll just do a couple, I think. Right, if you could put your compasses to a 3-inch measure. It's because of John Michell that I've sort of become converted to imperial measure, because I was born in 71, so I was taught metric. But yeah, John Michell's cosmology work, I think really, I mean, if the stuff that he shows is a random coincidence, it's one hell of a random coincidence. You need to look at his diagram if you haven't seen it, because it's really quite amazing what it does when you bring the mileage measurements for the Earth and the Moon into the equation. Right, I'm going to go into the middle of the page with my 3-inch measure and draw a circle. Now we're going to divide the circle into, actually, I'm just going to get a bit of paper to put below here because the light, um, yeah, the light goes a bit funny if I don't have white paper exposure on this number. It sort of calms the camera down a bit. That's better. It's a bit more visible now. Right. So in fact, I'm going to show you that whole square root of 5 plus 1 within this actual division of the circle. I'm going to place a horizontal line through the circle, well, through the center of the circle. That's really the key thing. Now, with the same radial measurements that you drew the circle with, I'm going to make a mark, one above and one below, and then do the equivalent thing on this side. So I'll get rid of that. Like that. Now, while we're about it, I'm going to use these two marks to get a bisector cross above and the equivalent one down below. And then hopefully this line that we put in will go through the center of the diagram as we have it. So now these marks that we've made become used for putting in these two lines like so. If you're used to geometry, you do a lot of geometry, then I can probably point out something here that might be of interest to you if you haven't ever seen it before. What we essentially have here is the division of the circle into six. So 1, 2, 3, 4, 5, 6. And so what we have here is the baseline of a triangle that goes that way, and that's the baseline of a triangle that goes that way. So that would be the Star of David. Just a little aside, we're not actually going to do that. We're going into 5 and 10, but I just thought I'd point that out in case you haven't noticed that before, if you're a keen regular geometer. Right, the thing about these points here is that, well, if we're drawing correctly, they should be the halfway point between center and circumference. So likewise, halfway point between center and circumference. So what should happen? Now, you see I'm saying should and it should be because I'm just accounting for the fact that, the human hand is at work here, which, may not have worked really accurately. What we want is to have a circle that goes through that circumference point and that center point. So obviously the point of the compasses needs to be at the halfway between them. So if you find that you aren't going through circumference and center as you want to, then you're welcome to move that point of your compasses ever so slightly using trial and error to make sure you're at the midpoint where you need to be. Goodness, we all need to be at the midpoint in these times of antagonism that seem to be going on in the world at the moment. The middle path is the only place to be. Or perhaps I should say that the middle path is where all of us actually truly are all the time. But sometimes we forget that. Right, I'm going to put a V shape in. Some of you who've worked with me before will recognize what I'm doing here. Now let's just take a little aside for a second, because I'm going to use this point here and this point here to divide the circle up. And let's just take a look, see how this, if this is 1, this is 2. So this line here would then essentially be that √5 line, which is required to get the golden ratio. Now, in actual fact, really 1 would be the measure of the whole radius. So when I say this is 1, it's actually 1 divided by 2. So let's just put the square root of 5 plus 1 divided by 2 equals 1.618. Now we can forget about the divided by 2, because the fact that I'm using just half of a radius means that we have the divided by 2 already. So all of these things here, 1, 2, √5, they're all half of 1, half of 2, half of √5. But you see how we have the square root of 5 plus 1, and it's already divided by 2. So that's how you get the 1.618. Now, if we were to do this, square root of 5 minus 1 divided by 2, that's equal to 0.618. So that's that other number, this one with 1 taken off it. And that's what we have here. So the square root of 5 minus 1, and it's already divided by 2. So that gives us this. So you can see how these 2 points that we're about to use are intimately connected to these golden ratio numbers. So let's actually, now before I do that, because we're dividing up into 10, I'm going to actually do the upside down V as well while we're here. Just to say, these 2 circles inside the larger circle, this is essentially how the yin-yang is drawn. So the yin-yang has this sort of golden ratio geometry within it. You can sort of see how if you use the upper semicircle here, you have one of them, and if you use the lower semicircle on the other one, then you get the yin-yang like so. Right, so I'm going to open up the compasses just a little bit, like so, where the V shape goes through the circle, and you should hopefully, if you're drawing accurately, you should find that it does the same thing on that side. I mean, to be honest, we actually hopefully will find that it does the same thing up here as well. Because obviously it's all the same stuff that's going on. Now there's one. And there's the equivalence, one like so. Now that gives us, now make sure you don't mix up these 2 points here. It's a very common mix up because they're so close to each other. Make sure you get the right ones, the ones coming off the arc. So here are 6 of the 10 points that we want. So this is 1/10 of the circle. From here to here would obviously be 1/5 of the circle. So having gone the square root of 5 minus 1, I'm now going to do the square root of 5 plus 1. And hopefully your compasses will make this stretch. Now I always like to put a sort of an eye shape in, so I go all the way down. We only actually need this here, this crossing here, but I just like to get the shape of the eye. My teacher, Keith Critchlow, used to talk about these 2 circles as being an image of Jagannath, who's Krishna, the Indian god. But like I say, all we need is just these crossings here. So this is where we get the other crossings from. And really, if you want to get the golden ratio, the square root of 5 needs to be in there somewhere. And of course, 5 is the number that, the symmetry of 5 is where you find the golden ratio in the pentagram, and so on. Right, now I'm going to put pinprick holes through these 10 positions. I'm going to go all the way through both bits of paper actually, because that's just sort of useful for having 3 different places where we can draw from. I'm only actually going to do 2 of the rosettes from that particular John Michell watercolor. John Michell was a very old friend of Keith Critchlow. Um, and in fact, in that book I showed you by John Michell, he sort of dedicates the book to Keith because Keith got John Michell into geometry. Right now, because I've got pinprick holes here, I'm pretty sure you can't see them. Let me see. I'll just so what I'm going to do is just draw. Actually, perhaps I will actually circle them. I might as well, just so you can sort of get a sense of what it is that I'm doing. So I'm just, you don't need to do this. If you can see your 10 pinprick holes, that's all you need. But because you probably can't see mine on my camera here, I'm going to highlight them just so that I can talk about what I'm doing. Now, in both of these diagrams, what I'm going to do is do a particular type of 10-pointed star where we skip 2 and go to the third. So my beginning point doesn't get counted. Skip 2, go to the third, and I'm going to keep on doing this. Now do these in faint line if you could, because these are construction lines essentially. We're going to put most of this in, but not quite all. So as you can see, every time I'm skipping 2. So here I skipped 2, went to the third one, skip 2, go to the third one. Now skip 2 and go to the third. And I'm just going to keep on doing that. This particular star is one that keeps on going around until it gets back to its starting point. 1, 2. So it sort of looks a little bit irregular as you start drawing it. So as long as you're following the counting, you can't go wrong. It's perhaps a very good description of sticking to the path, stick to the path, stick to the counting, and you'll be fine. You won't go astray. Now, obviously, to do that, I was looking at these points here. So what we need to do next is essentially the same star, but the points, the 10 points that we're working with this time are these crossings here. So this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So exactly the same thing. And what will happen is that each line you draw will be parallel with a line in the star already. So you can see if that's a starting point, 1, 2 goes to the third. And when this line goes in, you can see how it's running parallel with this one. So every single line you put in here should run parallel with one that is already in the main star. 1, 2 to here. And that obviously runs parallel with that one. And this is just going to carry on. One, two, three. So if at any point you're about to do a line that isn't running parallel with another one, What's your step? Right, I'm going to actually, having drawn fainter lines, I'm now going to go on to harder lead pencil. This is like a 3H I've used. I press a bit harder than usual so you could see it. But now I'm going to use an HB. Um, but if you don't have another pencil, just press harder when you do this. Now, I'm not going to go over all of these lines that we've drawn. Um, as you draw, you'll cross one line and then this middle area here, this is what I'm going to miss out. This is quite a conventional way of drawing this type of stuff. And within, we'll say particularly within the Islamic patterns, you often have this break in the line as you draw the central areas of stars. Now, as you progress round, you'll start to sort of have lines meeting and giving you these breaks. Right, I'm going to give the same treatment to star in the middle as well. So this first line here, which obviously reflects this one, I'm going to do exactly the same thing. So I'm going to start drawing, cross one line, and then stop there and leave this break in the middle. Now, in this particular rosette, the one remaining thing that John Michell did was just to put in, so you see where the angle comes in with the star, like so, just drawing lines through like so. So nice, simple ending. One's gone a little bit wonky, I have to say. I'm only human. And if I hadn't got out of bed on the wrong side, all of those should be going through the same point. Right here in watercolor that I'm working from, it's these two and these two are this one here. Right, I'm going to do this one next, these two. And these make nice relaxing color exercises. Yeah. So I'm going to do the same star as what I did previously. So skipping one, two, and going to the thirds. I'll assume you've got the hang of that. Again, skipping one, two, going to the thirds. One, two, going to the third. If you're working on the opposite side of the paper from the pattern that you just drew, you can probably see the one below through the paper. But it's always good to do these things more than once. Now, we're not going to do the second smaller star inside the first one this time. That's just what happens with the rosette that we just did. Right, we'll give the same treatment to this star in terms of using a stronger line. So the same thing as what we did before in the sense of there being this break in the line in the middle. And let's complete the star like that. Right, now some very simple lines going at this point. Again, using these inner angles of the star, these ones here, which is well, what we used in the previous diagram to draw the second star. But this time I'm just actually going to put in lines like this going all the way through. Right, now to finish off, there's a really nice little producing of pentagons at this point. Now again, these inner angles that come in from the star, so these ones, which I suppose you could say are the beginning and termination points of the lines that we've just put in. So these points here, I'm going to line my ruler up so that you have one, miss two, and go to the third, like that. And I'm just going to put a line in the middle, like this. So you end up getting a pentagon. Now, having used this point and this point to do that, I'm now going to use this point and this point. Do the same thing here, and you can work your way around. There's another pentagon. You can gradually work your way around, and what you gradually start forming here is a decagon. And this is one of the qualities of the decagon and the pentagon. 10 pentagons fit neatly around a decagon. Okay, ladies and gentlemen, I'm going to just quickly go back to my slides for a second. I still have a few places left on this course, so get in touch if you want to come on it between Palm Sunday and Easter Sunday. The next one of these sessions is going to be on the full moon on February the 24th, which will be Saturday in a couple of weeks' time, and that will be 12 midday. The full moon is at 12:30, so we always begin sort of within the half hour before the actual moon. So I hope you've enjoyed that, everyone. I'll put this onto YouTube, as I always do with these sessions, and I hope I'll see you in a couple of weeks' time. Have a good 2 weeks.
Thank you.